Okay, so welcome everyone to the Introduction to Robotics Part 2, which is mainly about kinematics of mobile robot. And to begin with, I will briefly introduce some mobile robots with different wheel. And, and I want to let you know that I will go deeply for particular mobile robots such as omni-wheel mobile robot and mechanism wheel because the kinematics of this type of robot is very easy because this course is just introduction. I will choose the easiest one for you. And so for the first part of this kinematics, uh, for this 1 hour lecture, I will be covering only 3 points: introduction, frame and coordinate system, and review of coordinate transformation and rotation matrix. Okay, let's see some mobile robot existing uh, in many applications. The first one is called differential drive wheel mobile robot. It has just two wheels, and these two wheels are just normal wheel, right? Normal means it's just like a motorbike tire, right? It's there's not, no mechanism on the wheel itself. Okay. For this type of robot, uh, it can have flexible maneuverability, so it can go straight. It can rotate around itself, and of course, it can go backward or forward. And to control this kind of robot, you just need to control the velocity of the two wheels. So there must be two separate actuators. And for this picture, it's a very common robot as well. It has four wheels, and sometimes you may use just two actuator. Then its kinematic is much like differential drive wheel. Yeah, of course, not exactly the same, but because it only has two wheels with actuator, then more or less the kinematic is very similar. Um, but sometimes people may also use four actuator on the wheels to have more power. Um, the next one, for this one, it's much like the previous robot, but the maneuverability on the wheel has more degree of freedom, so it can move up and down, and the angle of the wheel can be changed like much like a steering wheel. And for this one, it's called a car-like robot, so it has steering to change the angle of the front wheel, and the rear wheels have differential drive. If they if they are actuated, you need to have differential drive mechanism in order to have different velocity of the wheels. Okay. Why this is important? Because when you want to rotate, for example, in this way, this wheel must have slower speed, slower velocity. Okay. Um, but sometimes it can have the actuator for the front wheel. Then the rear wheel, you can just let it free, uh, free running, right? The shaft for both wheels are separated. And this part it's about a mobile robot that are very popular for research because kinematic is easy. Um, so this one is called omni-wheel with four wheels. Okay, this is also omni-wheel with three wheels. So actually you can have multiple wheels as you like, but the arrangement should something like this. That means the axis of motor should cross the geometric center of the robots. Okay, something like that. So we look from the top view. You have the center here, and then the axis of each actuator is like this. Okay, and for this one, if you look from the above, you can see a rectangle like this, and the axis of the motor should be like this. It's just a convenient way for deriving kinematics equations. Okay, so of course you can have more wheels if you want more power. And this one mechanism wheel. So mechanism wheel arrangement is very much like a normal wheel, but because of the some roller on the wheel uh, with proper arrangement, this robot can move sideways, okay? Can move forward, can move sideways, and can rotate, right? And I will be focusing on these two robots, Omni wheel and Mechanism wheel, and they both actually have the same mathematical kinematic equation. It just you need to choose the right angle of roller and some coordinate frame. So the next point is about frame and coordinate system. So first that you need to have is global frame. So H and Y. Global frame means a frame that is fixed with the environment, or you can say fixed with the how say the yeah. If you are talking about a robot that do exploration, then the global frame should be the planet itself. If the robot walk on the ground of the Earth, then the global frame is on the Earth. Okay. If the robot is exploring Mars, then the global frame should be fixed with Mars. And the next frame is the body frame, the frame that is attached with the body. So it means the moving frame represent the moving body, right? So the way you configure uh, how the body frames rotate with respect to the global frame by the angle psi here, which is the angle between x-axis of body frame. So I call this body frame, I should write B like this. Yeah, later you will see HB instead of H arm. Yeah, H arm can represent robot. Okay, and most of the time uh, in the robotic society we choose x-axis as a direction of the forward motion. Okay, so that's why H is here. Then the orientation of the robot with respect to the global frame is psi, and it has its center and uh, to represent the position of the robot itself with respect to the global frame. So when we talk about a point on the robot, it can be physically attached to the robot can be virtually attached to the robot in this way. Virtually attached means if robot moves forward, this virtually attached point also move forward. Okay. Yeah, this is very important when we need to derive the kinematic equation. Then the next point, which is very important, so the motion of the robot can be decomposed into two different motion. One is translation. So in order to have the position of the robot here with this orientation from the origin, so let's say the robot at the initial time it has this position and orientation. To move to this point and with this orientation, you can say that first you just translate it like this and then you rotate it, okay? Or you can say first you rotate it and then you translate to this position. So because this with the operation plus, it means you can have mathematical expression for this term and for this term, and you can add them. Okay. So yeah, because the rotation motion is complicated, the point that we define on the body frame and then we need to transform into global frame is not simple. That's why we need to focus for the rotation first. For the translation, it's very easy. Okay, it's just linear motion that you have learned since high school. So okay, now for the rotation, the trickiest point is about rotation of the robot itself. So let's say I have a point P virtually attached to the body frame, to the robot. Let's say H1 here is HB and YB, the body frame. Then point P can have coordinate, yeah, just say 1, no big deal. It has coordinate on body frame and also have coordinate on global frame. So how can we transform the coordinate from the body frame to the global frame if we know the orientation, angle, psi? Okay, how we transform that? So it means yeah, we know this one and we know this one. How can we find H should be, yeah, how we can find H here, which means from here to here, and YP here from here to here. Okay, so by using geometry it's very easy, right? Actually yeah, this one is H 1P and this one is Y1P. So here you can have HP YP equal to, so yeah, H1P here and Y1P here. And what is filled in here? What should be filled in here? Yeah, this term. Cosine psi, sine psi, minus sine psi, and cosine psi. And this one is called rotation matrix. Yeah, you can verify or recheck by yourself. But I'm going to show another way, which is we use Rgb Bridge Method, which is very convenient, easy to remember. You don't need to draw too many many geometry in here. So let's say you have 1P here, then you can have coordinate 1, and so the vector from O here to the point P here has coordinate on the global frame, again HP, yp. I say vector first. Okay, let's say O P equal to from O to this point, which means H1 itself, H1P itself times unit vector UH. Okay, UH1 and plus this vector, which means the Y1P itself times unit vector Y1, right? Now I rewrite it in algebraic form. So OP is um, actually just HP YP. Li hua từ lục một tí cho này. Okay. And here we can write in the algebraic form. So we have H1P here, 1P here, and UH1 here, which is a column vector because UH has a component on x-axis, right? Cosine psi and sine psi. And this vector UY1 also have coordinate on the global frame, minus sine psi, cosine psi, right? So this is column vector plus y1p times uy1. This is column vector. So you rewrite this in the algebraic form. You can write like this. You want to take h1p and y1p here. So how you can have here? Yeah, what you have here is uh1 here and uy1 here, and they are column vector. And what are these vector? This vector UH1 has component cosine psi, sine psi, and then for this unit vector y1 on the x-axis, it has minus sine psi, cosine psi, right? So this is rotation matrix. Okay, so this one is y1p, y1p. Okay, this one is rotation matrix. Right? So as long as you know psi and you know the coordinate that is fixed on the robot, you can always you can transform the coordinate into the global frame, okay, of the vector from the origin of the robot to the point on the robot, okay. So let me rewrite here for this one. Let's say we want to find a point P virtually attached or physically attached on a robot. Let's say this point. Okay. So the coordinate of this point P, we say HP here, YP equal to. Now we also have translation from O to OB here. So from O to OB, we call it H and Y. So H and Y is the coordinate of the origin of the robot itself. So it has H coordinate, Y coordinate on the global axis. Plus, for the rotation part, we just have rotation matrix in function of psi and times the coordinate of the P on the robot frame, which is H. In this case, in this case I use R, so it should be HRP, YRP in the robot frame, or sometimes just write it as HB like this, okay, HB YB. So no big deal, right? So here rotation, this is translation. And all right, so in here we can see the complexity is on rotation matrix itself. Then we should know some properties of rotation matrix in order to deal with differential with the kinematic equation and differentiation. So first, determinant of rotation matrix. Yeah, because this is just review. I think you may have learned this before. But anyway, determinant of rotation matrix, even in the 3 dimension, is always 1. Okay, rotation R is 1. You can check by yourself. Just have cosine psi, sine psi minus sine psi, cosine psi. Yeah, determinant, right? Determinant of this cosine square plus sine square equal 1. What if rotation matrix in 3 dimension? It's also 1. The determinant is also 1. Okay. But first, how you can construct a 3-dimension rotation matrix? Now let's view the rotation matrix here in a 3 dimension. So for the x and y, you have z on the axis that is perpendicular to the screen, right? And h1 and z1 also perpendicular to the screen. So z just coincide with z1. And use this method to find rotation matrix. Actually, rotation matrix, you just put all the unit vector of the body frame like this. Then you get the rotation matrix. If you notice this, right? This one. So it's very easy, right? Rotation matrix for the 3D, 3 by 3. You can have UH1, UY1, UZ1. That's it. So what is UH1 and UY1? UH1, as you see here, UH1, it have coordinate on the global axis, cosine, sine, and what about its component on the z-axis? 0, right? So cosine psi, sine psi, 0. How about y? Yeah, you can just take this first, minus sine psi, cosine psi. How about the component of uy1 on the z-axis? 0. And then the unit vector on the z-axis itself, uz1. Okay, uz1. So uz1 has a component on the z-axis only, right? So it should be 0, 0, 1. And then you checked, determinant is still 1? Yes. Take this and time its cofactor. So 1 time determinant of this, right? 1 time determinant of this, because determinant of this is 1. So still determinant of all 3 by 3 is 1. Okay, always. Even rotation in arbitrary axis, rotation matrix always have determinant 1. Why? Because no matter how you rotate your frame, the norm of this vector is 1, norm of this vector is 1, norm of this vector is 1, and all the vectors are perpendicular 2 by 2, right? You can check by other means. Okay, next, rotation matrix inverse. Well, because it is very special, we can see that rotation matrix is composed by unit vector or two or three unit vector which are perpendicular to each other, and this unit vector have unit norm, unit length. So if you are very familiar with orthogonal matrix, actually not just orthogonal but orthonormal, then you will be interested to check what is R transpose R, right? So R transpose R is, yeah, you check cosine psi, sine psi, minus sine psi, cosine psi. Okay, just remember cosine and then minus sine cos because these two are perpendicular. And oh, you transpose it. Yeah, you transpose. So here cosine psi, sine psi minus sine psi, cosine psi. You transpose it first, so I should rewrite like this. The minus sign should be here, and this one I can erase the transpose. So cosine cos square, sine times sine square, then you can have 1 cosine times minus sine plus sine times cosine, so you got 0, minus sine times cosine plus cosine times sine, you got 0, minus sine times minus sine, sine square, cosine times cosine, cosine square, add together 1. So this is just identity. If the identity, it means R transpose equal to R inverse. Then R transpose equal to R transpose equal to identity. Okay, this is very important property for the rotation matrix, and you must remember. Okay. So are you still familiar with this, Adrian? Property of rotation matrix? Yes. Yeah. And the next one, how about rotation matrix of uh, two vectorial vector? So R times C, R times R A cross B. So can you give me a result, Lucas? Sorry? Can you give me the result of this? What will it be? The result of this? Yeah. What do you consider A and B? A become RA cross RB. Cross RB. Okay. Okay. So why is this? Why is that? So yeah, I think this can be yeah, if you remember it's good, but if you don't remember, you may get confused, right? So I'm going to explain a little bit here. So let's say if you have A and B vectorial, then you got C like this. So yeah, when we apply rotation to all the frame, to the whole frame, right? Then which means A is here. Oh no, all A is here. Then RB is here. Then RC is here, right? So when we apply to here, which means we apply R to C, but RC must be equal to RA vectorial or not like A here and B here, right? Okay. And the next point, time derivative over rotation matrix. And so rotate. Okay, the time derivative of rotation matrix. Can anybody give me an answer? Equal to 1. Masang? Masang, you still remember? Can you share with your friend? Masang? No, remember? Okay. So actually, there is a way to prove this very nicely apply to any arbitrary rotation method, but I will just show by a trivial method specifically for the rotation method that we saw here. Well, so we can start. Okay, let's say now we have R is cosine psi, sine psi, minus sine psi, cosine psi. Then we take the time derivative just to see. I mean, we use a brute force. No, not brute force. It's a trivial method. Just so we can get this one here like this. This one is minus sine psi. This one is cosine psi. It's minus cosine psi. And here is minus sine psi. And this one, it's called the angular velocity of the rotation method itself. So maybe you will say, how can we come up with this expression I'm going to write soon? Actually, this one is just 0 minus omega 0 0 0 0 0 0 times the original cosine psi, sine psi minus sine psi and cosine psi. Yeah, you may question, how can you come up with this multiplication? Yeah, right? Yeah. This one? Yeah, this one should be what? Ah, yes, you're right. So wait. So yeah, 2 by 2. Yeah. I think right. I cut out this, right? Yeah, cut out this. So it doesn't seem right. This one minus. No. I think minus is here. Minus is here. Yeah. Okay. Yeah. So well, yeah. You will know why I immediately write the 3 dimension, right? Yeah, because there is a way to prove that rotation matrix derivative of rotation matrix is omega tilde angular velocity tilde times or cross omega cross r. So I should say this one is omega z. So this one is omega z to be. So it means this one is 0 0 omega z, right? Like this. Because of this formulation, that's why I know that we can write like this. Okay. Yeah, if we study the rotation in the 3 dimension, I must show this to you, but because we don't need We don't need that, right? We just need to remember this. Okay, I don't need to show it. Um, so what you need to remember is this, and actually, its formulation can also be write like this, or times omega prime cross like this. Okay? In our case, it's very special that omega prime and omega is just the same because the z and z1 axis are coincided. So no big deal. Just choose this one. And so here, how do I fit this 3-dimension to this 2-dimension? I mean, using this formula for this 2-dimension. Yeah, I just showed you earlier that we can construct a 3-dimensional rotation matrix because rotation in the plane HY has the same meaning of rotation around the z-axis. So we have 3 components. So actually, this formulation is from so R dot should be R3 equal to omega cross R3. So this, because this omega has only, so omega cross, I will write in full formulation first. Omega cross is skew symmetric matrix with this one the omega z, this one minus omega z, this one omega y, and this one omega minus omega h, and this one is minus, oh no, this one minus, this one plus, this one is minus omega y, this one minus omega. What's wrong with me? What's this? Minus. So he should be omega h. No, minus here. This one plus, okay, and minus omega h 0. So each row has only has minus sign only one. Okay, each row, and for the row of h there's no omega h. Row for y there's no omega y, and row for z there's no omega z. So it's easy to construct this. And times rotation matrix cosine psi, sine psi 0 minus sine psi cosine psi 0 0 0 1. Okay, then you can have you can have, what is this, minus sine cos minus sine, minus sine psi minus cosine psi, and here cos psi minus sine psi 0 0 0 0 0. Okay, like this. And then you look at the 2-dimension here. The 2-dimension here must be the same as here. Here. Oh, I missed something. I think I missed something. I miss psi dot. Yep. Okay. Which is omega z. Just straightforward to omega z. Okay. What I'm trying. I must say refers because omega, yeah, since omega equal to 0 0 omega z. Okay, to validate this, right? Omega h is 0, omega y is 0, because no rotation in the plane y, there's no velocity, angular velocity component on the x and y, but only on the z-axis, right? Rotation like this, it means the vector representing rotation is like this. Okay, so yeah, it's almost 1 hour. You can have a break for 5 minutes. So at 6 past 10 we will restart.